Okay, so let me remind you what we were doing yesterday. I'll start with the GeoGebra animation that I had shown you before. Let's see. Okay, so what I was telling you yesterday is that, okay, now we're talking about interpolation. Let me see if I can check the chat just in case there are any questions. Okay, so when we're talking about interpolation means that you have like a number of points. You can think of them that they're like experimental data or whatever you want. And so you have like a number of points and you want to try to find a curve or like the graph of a function that passes through all those points, right? So in the particular case that we were discussing yesterday, the idea was to just to like try to find a polynomial that passes through the points, just because polynomials are easier to understand. There are many nice properties that we know about polynomials. So, like for example, in the animation that I was showing you, like yesterday, what we were doing towards the end of class is like if, say, for example, you had three data points, which are like these ones that are called like ABC on the GeoGebra animation. Kind of like roughly the rule of thumb, if you're trying to find like a polynomial, is that if you have three data points, you should aim for a quadratic polynomial. So it's always like 1 degree lower than the number of data points. Okay, so you're trying to find a quadratic polynomial that passes through them. So the idea of the Lagrange interpolation, the way it's set up, is that what you do first is, and that's kind of what I'll write in more detail today. What you do first is you find a polynomial of degree 2 in this case that passes through one of the points and is zero at the remaining 2 points. So for example, like let me show you the blue one. So if you look at the blue polynomial, it passes through point A, but at the x values for B and C, it vanishes. Okay, so it's passes through one of them and it's a root. The other two x values are a root for that particular polynomial. And then you kind of do the same for the other two. So for the red point, you want to find a polynomial that passes through that particular point, and at the x values of the other 2 points, the polynomial is zero. So this is the one that you see here. So it passes through here, red, and is zero at the x values of blue and green. And similarly for the last one, um, then you find a polynomial that passes through the third point, the green one, and for the at the x values of the blue and the red points, it is zero. Okay, so it's kind of like zero almost all at all the points except one, and at that one it passes through that particular point. Okay, and the reason for setting it up that way, so these are like the three polynomials, is that once you have set it up with that particular property, if you just add them together, um, you know, if you add them together, then you will get the polynomial that passes through all the points because, um, since like it's always zero almost all the time, so like it kind of like will have like the desired property of passing through like each of the points. Is that making sense? So I'll kind of write that down like like kind of like the general formula. But once you kind of like see that idea, it's not too bad to construct them. It's like actually pretty straightforward. It's just kind of like having the right mind frame for how to build them. It's just like to give you like the general formula. I do have to start with some like detour first, a little bit about notation to have around. Since I don't know if everyone has seen the product notation, and it is like a useful notation to have like available. So like I'll start with that. Once we have discussed the product notation, I will kind of like give the formula for the polynomial in full generality. Okay, let me stop sharing my GeoGebra and move to the iPad if that sounds good. Okay, so as I was saying, we'll continue talking uh, about the interpolation stuff. But first, I want to just introduce some notation. Okay, first I'll put one that you are familiar with and we have been reusing already, which is like the sum notation, right? Like with the sigma sum not but it's kind of like a good thing to have them side by side so that you can contrast them. So the sum notation, it's something like this, right? Like for example, if I write like sigma of like let's say I equals 0 to 3 of x plus I. What does that mean? Like you just give I the values 0, 1, and 3, and then you just like sum over that, right? So like it would be x plus 0 plus x plus 1 plus x plus 2 plus x plus 3, right? Like that would be the you like the index. That's usually how you would refer to I. The index is just like allowed to change from 0 to 3, and in this case, like you just add them together, right? So in this case, like the answer would be what would be the answer? There are four x's, so you get 4x, and then 1 plus 2 plus 3, that's just 6, right? So that, and again, like that's like a notation that definitely, at least in Calc 2, you would have seen, and even I think in differential equations, right, when you're solving differential equations, like using power series. The one that I'm not so sure if everyone has seen before, that's why I wanted to mention it, is the product notation, which is also convenient. It is the same idea as the sum notation, but you just multiply instead of like add. Okay, so and for the product notation, you use kind of like this symbol. I think that's like an almost like an uppercase pi, if I'm not mistaken, in the Greek alphabet. I would have to double check that. But I'll do it first for this example so that you see like the difference. So the idea is like instead of like adding the factors, you just multiply the different factors that you get by giving different values to I. So in this case, it would be x plus 0 times x plus 1 times x plus 2 times x plus 3. Okay, and then again, the I is changing from 0 to 3. Is that okay? Is that making sense? Kind of. In this case, like, there's not much that you would like to do because you don't want to do all like the product explicitly. The only thing I would do is like rewrite this as x times x plus 1 times x plus 2 times x plus 3, right? But like there, if you were to do all the multiplications, like it's actually nicer to have like the polynomial factor, so it's more convenient to leave it that way. But I just wanted to kind of like compare it, with with how the sum notation would look like. Here's like another one, like, you could do like, I mean, it doesn't have to involve x, you could do kind of like the product of I equals 1 to I equals 4 of I squared, right? So what would that be? It would be, you'd start giving different values to I, so it's 1 squared times 2 squared times 3 squared times 4 squared, right? And again, this is I taking different values from 1 to 4. And so that gives you what? 1 times 4 times 9 times um 16, right? And then like I even myself have to do this like, so what does that give you? It gives you 4 times 9 times 16. If you multiply it out, it's 576. So obviously, like in the product notation, like because it's multiplication, if you were working just with numbers, like that will be seen in general like even way bigger or way smaller than just adding them, right? Like depending on whether the numbers are greater than 1 or smaller than 1. So it's like it's kind of like set up in a very similar way to the sum notation, but like obviously what you end up with will be very different. Is that making sense? Like this notation kind of like reasonable? Any questions about it? It's just going to be convenient to use it like in a couple of minutes when we kind of like write down. the the polynomial. So it's I just wanted to have it around. Um, Professor Good, any questions about this? Yeah. Okay, and the other thing in terms of notation before I write down the formula is the Kronecker symbol, which I don't know, like maybe another thing. It's convenient to have around as well. Okay, so the Kronecker symbol, usually the way you write it is like as delta ij. Okay, so this is like okay. There are two ways to think about it. Um, One way is that it just like refers to the entries of like the identity matrix of a given size. So delta ij, one way to think about it is like the entry in row I, column j of the identity matrix of a given size. So for example, what is the 2 by 2 identity matrix? Let me just write it like this. What is the 2 by 2 identity matrix? It was 1, 0, 0, 1, right? So in this notation, like again, this would be what delta 1, 1, delta 1, 2, delta 2, 1, and delta 2, 2. Okay. Let me do another one. So what was like the identity matrix of size 3 by 3 is 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And so this would be delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 2, 2, delta 2, 3, delta 3, 1, delta 3, 2, delta 3, 3. Okay. So the Kronecker delta is, or well, sometimes it's also called the Kronecker delta, but the Kronecker symbol is just like a way to refer to the entries of the identity matrix. In practice, you kind of like think about it more concretely because if you see, there's kind of like a distinction, like the values are either 1 or 0, right, for the identity matrix. So kind of like the way to think about it, which is more convenient, and that's usually like the definition you'll see for the Kronecker symbol, is that if both indices match, like 1 1 or 2 2, then the value of the symbol is 1. Or like similarly here, if you notice like 1 1 2 2 3 3 give you 1, and everything else gives you 0. So kind of like the usual definition of the Kronecker symbol is that delta ij is just 1 if I equals j and 0 otherwise, which kind of like summarizes like more conveniently like you know what I have been writing. Is that making sense, kind of? Questions about like the symbol, how it's written down? So the reason why you use it is because it just gives you like a more elegant way of like sometimes writing certain formulas. So let me give you an example of like sometimes how certain formulas can look more like nicer. Okay, like I'll give you like an example of multivariable calculus. Like just to kind of like see how like it's more simplifies like the notation like a lot sometimes. So here's an example from Calc 3. Okay, so like like you probably remember partial derivatives, right? So for example, like if you remember, like what is a partial derivative of like I don't know, like x squared with respect to x, that's just 2x, right? But what is a partial derivative of x squared with respect to y? That's 0, right? And what is the partial derivative of x squared with respect to z? That would be 0, assuming like that you're working on R3 so that there are only three coordinates, right? That's how like the partial derivatives would work out. Okay, so kind of like a better way of writing this out is instead of like using x, y, and z, let's call the variables x1, x2, and x3. Call them x1, x2, x3. Again, just because that allows you to generalize more nicely. So from that perspective, like the same formulas that I just wrote for the partial derivatives would become the derivative of with respect to x1 of x1 squared is to x1. The derivative with respect to x2 of x1 squared would be 0. And the derivative with respect to x3 of x1 squared would be 0 as well, right? It is just like a change of labeling, right? Like it means the same as before. But if you notice, like that requires you to write it down using three different, like you have to write it down with three separate equations. But if you have the Kronecker delta or the Kronecker symbol around, you can just kind of like summarize all that information as a single equation, because then you can just write how would this read in using the Kronecker symbol? You would write, well, the derivative of with respect to xi of x1 squared would be 2 xi times delta, let's see, delta 1 I. Because like the only like if it's kind of like take some time to convince yourself that that means the same, but kind of like what this is saying is that like it's always easier to think when it's the 0. So if the variable, if the index is not 1, right, if the index is not that 1, that gives you 0, and now automatically whatever else you had is 0. Okay, so and if the index is 1, delta 1 1 is 1, and so this becomes delta 2x1, and then it had to be here x1. So it's kind of like and again, it's not we're not going to use partial derivatives too much, but I just want to kind of like show you how it can be convenient, because like three equations are kind of like very succinctly summarized as like a single line in a single line. So like this means the same as the previous three equations. Means the same. But and what's even cooler is that like that gives you like a generalization, like like then you could have like any number of variables and it would be the same equation representing all those equations, like you see with the Kronecker symbol. So like it is just like a very convenient gadget to have around to kind of like rewrite certain things in a more like kind of like simplified form, instead of having to express everything like very, very like in very long format, which is kind of like the same as vector notation. Like, that's how all the point of like vector notation is like a similar idea. It's just like a nicer way to represent like the data. Uh, is that okay? Questions about this so far, so good? Okay, so now I can get finally to the formula for the Lagrange polynomial. So I'll kind of like just remind you what the setting is, and I'll then write down the formula, and you'll see that it is very convenient to have all this stuff around, all this extra notation that I just gave you to kind of like write it in a very simple way. Okay, so again, the idea of the Lagrange polynomial, like the Lagrange interpolation formula, So again, like kind of like the, let me write down the input. I'll write it more like an algorithm. So this would be the input and the output. Okay, so the input is going to be n plus 1 points. So it's going to be n plus 1 points, which are called x0, y0, x1, y1, up to xn, yn. Or if you prefer, like again, like just to get used to the index notation, like you can summarize them all like alternatively, or like xi, yi, where I goes from 0 to n. Okay? Again, that's kind of like the more elegant way of like writing the same thing. Okay, so the input is a number of points, right? As I was saying, the output that we want to produce is like called the Lagrange polynomial. So the output is going to be, it's going to be a polynomial of degree n. At most n, because like there, you could still have like these situations like the one I mentioned yesterday, where I gave you 3 points, but the 3 points happen to be on the same line. So like the polynomial would end up being like a line, not like a parabola or something like that, of degree at most n. Which I'll just call it ln of x. And so it's a polynomial of degree at most n, which passes through all these points. Okay, which passes through all these points. So again, what does that mean in practice? In practice, that means that ln of x0 would be y0, that ln of x1 would be y1, dot, 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 that ln of xn would be yn. But again, it's all, like nicer to just write it using the indices, or if you prefer, you can just write it as saying that ln of xi equals yi. That is kind of like the same thing. So if you give it the value of the x coordinate of a point, it will return the corresponding y coordinate for that data point that you had. Is that okay? So far, so good. Is that making sense? Like the notation and everything. Okay, so the main idea. Um, Let me write down the main idea. The main idea is to solve this. You do what I mentioned at the beginning. So you just find for each point, you find a polynomial that that it passes through that point. Okay, but kind of like the way we will set it up is a little bit different. Like so, for each point, I'll find a polynomial that is one at the x value. Okay, and then we will rescale it with the y value to have that property. Okay, so the key step is that for each point xi, yi, you find a polynomial. Okay, and I'll use this Kronecker symbol to kind of like summarize the main property of this polynomial. That's why I was like referring to it a bit earlier. So the idea of this polynomial is that if you give a value at one of the x values, of the data points. Oops, sorry about that. Like, let me. Can you see it again? Like, I think the iPad got so disconnected for a second. Um, so if you give one of the x values of the data points, it is the Kronecker delta. So it is basically what that means is that it is exactly one at xi and it's zero for all the other x values. So. So, for example, like maybe it's useful to have like some concrete example before I continue. Like like yesterday, like I was giving you, like yesterday the data points were like the data points were let's see, there were 1, 3, they were 3, 5, they were 5, 6. Okay, so this is what I would be calling x0, y0, x1, y1, and x2, y2. Okay, and the idea is that the three polynomials that I'm talking about in this notation, the polynomials, so here like n is 2, right? So the three polynomials I'm talking about is like L20 was x minus 3 times x minus 5 divided by 8. I'll use the same colors as the GeoGebra animation. I'll post the GeoGebra animation actually on Canvas if you, or like on GeoGebra if you want to play with it. And then L21 was um, x minus 1 times x minus 5 times negative 4. And L22 was x minus 1 times x minus 3, divided by 8. So it's kind of like it's like from here you can kind of like check what I'm trying to say. So what I'm saying is that if you look at this polynomial, like the twos just refer to the degree of the polynomial. So that's just saying that it is going to be polynomials of degree 2. That the number after the comma is referring to which point is each polynomial associated to. Okay. So for example, what this saying is that this is associated to point 0. Point 0 is here. Okay. So if you notice, if you put x equals 1, if you put x equals 1 here, you get 1 minus 3 times 1 minus 5. So you get negative 2 times negative 4. So you get 8 over 8. So if you put 1 here, you get a 1. And you get 0 for all the other values of the x's. And same goes with the other ones. So this one is associated to this to point x1, y1. And so the idea is that if you plug in this value of 3 here, if you plug in x equals 3, this will give you 1. And if you had plugged any other of the x values into the formula, then it would give you 0. Okay, so it's kind of like a switch, like, it turns on at the value xi and it's turned off at the value at any other value. Okay, so they're kind of like activation polynomials, like if you want to think about it this way. So like the L, kind of like the idea to have like a metaphor, like to in your head is like, that the polynomial activates uh, activates at the value xi. It's kind of like turned on, like and it's turned off, right? of at any other values. Is that making sense? Kind of like what I'm trying, like how I'm writing down the notation. Like honestly, like understanding the notation is like the most important part here because like if you get the notation, then like everything else like will be fine. So in this case, okay, so kind of like as I was saying, the key step is to find these polynomials because if you found these polynomials, you know, assuming that you find that polynomials, the formula for the desired polynomial, the Lagrange polynomial, is very easy. Okay, so if you find then the desired polynomial, and this is like the formula for the Lagrange interpolation polynomial. It's going to be Ln of x is just going to be the sum from I equals 0 to n of yi times ln I of x. Basically, you kind of like multiply each polynomial by the corresponding y value so that it gives you the correct y value, and then you just add them together, and that will give you the interpolation polynomial. So basically, it all boils down to finding these like polynomials. Okay. So this is what I will refer to as the Lagrange polynomial. And the idea is that what like that I kind of had mentioned before, uh, what was the formula for this one of these polynomials? Essentially, to find so the kind of like the key question is how do you find these ones? So how to find how do you find the polynomials? Okay, so basically what you do is that's what I was explaining you yesterday. What you can do first, if you like, is you create a polynomial that includes all the products of all the x values. So you kind of like you build like let me write it into two steps. You build step one, you build so again, what like this is like the product notation. This is x minus x0, x minus x1, up to x minus xn. So this is like a polynomial that is zero precisely at all the different x values. Okay, so this polynomial at all the different x values, and basically the idea is that once you have these, you kind of like remove one term at a time to have the. Let me just call it LX just to make it nicer notation because it has like 1 degree higher actually. Okay, so once you construct this one, you remove one term at a time, and basically that will be the one that you are after you rescale it. So the formula for ln I, I'm about to do another example to show you how it looks like, so that you have another one. But you'll see that it's relatively straightforward to find them. it will be the product. Oh, okay, let me, well, okay. So what I mean by this is that the numerator, this numerator is, this is the polynomial Lx without the term x minus xi, basically. So you just remove one of the terms and then you kind of like divide by the value of that polynomial evaluated at xi so that it kind of like gives you one, basically. I'm about to do an example with 4 points so that you see it more concretely. But that would be again, like it takes some time to get used to all this notation, but you don't have to think about it in terms of the notation. If you understand the procedure, it's actually not too bad to find them. Okay. So let me go to back to GeoGebra and I'll show you another example. Okay, let's see to find it and but from scratch without using all these the notation so that it's um, less confusing. So let me choose like 4 points. So I'll do -1, 2. I'll do 0, 0 just to make my life easier. I'll do let's do 1, 3. Okay. And I'll do 2, 0 again just to make my life easier. Okay. So those are the 4 points. Okay. And I want to find a polynomial that passes through all of them, if that sounds good. Uh, because I have 4 points, I will try to find a polynomial of what degree? Degree 3, right? So that's what I would like to do, and I'm going to write it down now. I'll do it on the iPad so that you can see how you would do this. Okay, is that making sense so far, so good? So let me write that. Let me write down the points, and I'll kind of like try to match the colors. Um, well, remember, it's always 1 degree fewer than the number of points. Like the easiest way to think about it is if you had 2 points, right? If you had 2 points, you would find a line, right? You wouldn't find like a parabola. Yeah, yeah, that can be also confusing. But it's always like 1 degree lower than the number of points. It can even be less than that, right? Which is kind of what I said yesterday. Like because I could give you 4 points. If I give you 4 points that happen to be on a line, then you're not going to expect a degree 3 polynomial. You would expect a line, and it will be correct. Like if you use this algorithm, it will produce a line. It won't produce something wrong. Like so, it does produce a correct answer. Um, okay, so let me give you the example because once you see the example, it's super easy to kind of like not know what's going on. So, so find uh, the Lagrange polynomial. I'll just use the same colors to the one on GeoGebra to match everything. So like it would be through -1, 2. Okay, so again, that is uh, I'll put below what it's supposed to represent in our notation. 0, 0, that is x1 y1, right? And then 1, 3, that is x2, y2, and last one would be 2, 0. Okay, that would be x3, y3. Okay, so that is like in our notation, um, the 4 points with how they're referred to in terms of indices. Okay, so kind of like the most important step is simply to construct this polynomial that kind of like is zero at all these x values. So the big polynomial, like this is what I was telling you yesterday. If you want, you can call x just like a vector whose entries are the different x values. It's just a useful notation to have, you know. Um, so it's kind of like a vector of like the x values. Okay, and so from this, using this notation, what I was like writing a couple of moments ago is that this first polynomial that you start with is just x minus each of the x values all multiplied together. So it would be x minus 1, right? Times x minus 0, right? Times x minus 1 times x minus 2. Is that making sense? And then you can simplify it a little bit. What does this become? It becomes x plus 1 times x minus 1 times x minus 2. So far, so good up to this point. And then kind of like the idea is that you remove one factor at a time. And that's kind of like the prototype for the polynomial. So for example, for what is L30 in this notation, it is what you get by removing the factor associated, this first factor, okay, is what you get here by removing this factor. So you get x times x minus 1 times x minus 2. Okay, but then where did I get 30? Where is 3 come? Oh, 3 is just to say that it is degree 3. 0 is to say that it's associated to the point 0. So this, let me write it down here. This is refers to the degree, and this refers to the point in question. So this is saying that you're going to find a degree 3 polynomial, and this is saying that what you're removing is the x0 from the polynomial. Is that making sense? So there's going to be, I mean, I can write the rest first. You know, there's going to be an L31, there's going to be an L32, and there's going to be an L33. Uh, no, let me see. Like, no, we use a parabola. Like these were like you know, like this is like the one from yesterday. So I had these 3 points, right? I created first a degree 3. Um, that's what I'm saying. Like, right, I created first a degree 3, but then if you notice, what I did was kind of like remove one at a time, which is what I'm doing right now. So they end up becoming degree 2. So yeah, like it starts at, you know, like the degree starts one higher, but then you remove one term at a time, and then it gives you the desired degree, if that makes sense. Is that okay? Um, Okay. Actually, let me put the numerators for all of them because that's a little bit easier to understand. So what I'm saying is that the way this is set up, each of them is going to be a fraction. Okay. Um, so for example, for L30, what you remove is the first factor because that's associated to 0. For L31, you remove the second factor because that's associated to x1. So if you remove this one, which is kind of like removing the x, right? You get x plus 1 times x minus 1 times x minus 2. Okay. And then for the next one, you remove the factor corresponding to x2. The factor corresponding to x2 was this one. So you remove this one from the polynomial. So you get x plus 1 times x minus 2. Okay. And for the last one, you remove the last factor, right? So you remove the last factor. So you get x plus 1 times x minus 1. Is that okay? Is that making sense? Like I'm writing them as fractions because there's still like a piece missing, but I just wanted to make sure like that the numerators are making sense. So each of the numerators for each of the polynomials is just get obtained from the bigger one by removing one factor at a time. Okay. And then okay, so why do you still have to divide by something? Because what happens here is that if you notice, like let's just start with the first one. What's happening here is that this polynomial, right? This polynomial is precisely 0, at 1, and at 2, right? That is 0 at all these 3 points. Okay. At -1, right? At -1, it won't be 0, right? At -1 is not going to be 0, but it's also not going to be 1 either. So I wanted to give me the value 1 at -1. So what I'll do is just like plug in -1 into this formula and then divide by that. So I'll plug in -1 times -1 minus 1 times -1 minus 2. And the reason for doing that is that kind of by default will guarantee that if I put -1 here, like everything will cancel out and then you'll just get 1. You'll just get 1 if that makes sense. So that will make it 1 at the first value for x and 0 everywhere else. 0 at all the other x values. Is that making sense? Like kind of like that rescaling? And then you do exactly the same for the other one. So for example, if you look at the next polynomial, this one is 0 here, it's 0 here, it's 0 here, right? Now the only place where it's not 0 is at x equals 0. So you evaluate at x equals 0 and to rescale so that it will give you value 1. So it will give you 0 plus 1 times 0 minus 1 times 0 minus 2. Okay. Let me create a little bit more space because I'm running out of it. Um, and then you do exactly for the same for the other ones. So for the other ones, for the green one is associated to value 1. So you put x equals 1 there. So you put 1 plus 1 times 1 times 1 minus 2. And the purple one is associated to x equals 2. So on the purple one, I'll put x equals 2 here. I'll put 2 plus 1 times 2 times 2 minus 1. And then, okay, maybe the next step is just like a little bit of arithmetic and simplification. So let me check whether to see if it's fine, like what how I wrote it down. Is it clear how it was constructed, each of them? And then like now it's just a little bit of simplification. So for example, for what is L30 x, then it would be x times x minus 1 times x minus 2. Let me see if I can do the arithmetic in my head. So this would be -1, this is -2, right? That gives you 2. And then this gives you -3. So 2 times -3 is -6. Okay. Then the next one, L31. By the way, if you know how to find the polynomials, I don't care how you call them, right? I'm just trying to give them some names so that it's kind of like some standard notation. But as long as you know how to find the polynomials, you don't even need to label them. You know what I mean? Like it's totally fine. I just wanted to give you something more like to keep track of, that could be useful. But sometimes like too much notation can also be confusing. So if you see the algorithm, it's kind of like clear step by step what you're supposed to do, so you don't have to kind of like be overthinking too much. What the notation is. So this gives you 1 times -1, that's -1 times -2, that's 2, and then L32 x is it is what x plus 1 x times x minus 2 divided by 2, 1, -1. So that's -2. And the last one, L33x, would be x plus 1 times x minus 1. And then this gives you what? It gives you 3 times 2, that's 6. Okay, and then this. Okay. So those are the four kind of like basic polynomials in this problem. So maybe before continuing, let me show you how they look like on GeoGebra. That's kind of convenient. Um, okay, so let's see. The first one, let me write down the first one. I'll call it P1 for first polynomial. I mean, I guess I think GeoGebra would let me call it P0. So it would be x times x minus 1 times x minus 2 divided by -6. Okay. Uh, so this one is blue. Okay. So again, you kind of hopefully see that it is 0 at the x values of the points B, C, and D, and it's 1 precisely, and it is 1 precisely at the x value corresponding to A. Okay, so it's kind of like turned on. It's activated at -1. It's activated at -1, and at the other x values, it's turned off. Okay, that's how you should think about it. Let me see if I can open up the the screen so that it looks a little bit like so that you can see the entire formula. Because right now, okay, now it's better because now it lets you see the entire formula for the polynomial on the screen. Okay, so that's P0. Then P1 is going to be activated at the x value for B, and it's turned off at all the other values. So it would be, according to the formula that we found, x plus 1 times x minus 1 times x minus 2 divided by 2. Okay, so that's P1. So you see, x plus 1, Yes. Yeah, yeah. The x value is one precisely at the x value for B, and at the other x values is zero. And then the other ones go kind of like similarly. So P2 of x would be x plus 1 times x minus 2 divided by -2. Okay, so this one should be green. Again, now it's 1 precisely at the x value of the third point and 0 everywhere else at the other x values. And the last one would be P3 of x, which would be x plus 1 times x minus 1 times divided by 6. And this one was purple, right? So this one would be purple. Okay, and then there you go. So it's activated at the x value for the last point. That's where it's 1, and it's 0 at the other x values. So those are the 4 polynomials, which are very nice. Oh, no, so these are not supposed to cross the points, but to make them cross the points, you just multiply by the corresponding y value. That's the idea. So these don't cross the points directly, right? Right, exactly. It's kind of like that's why the Kronecker symbol is useful. The thing is like working with 0, 1 is easier than working with the y values at first glance. But yeah, like so for example, this one is not passing through the point, but how do I force it to pass through the point? I just multiply by 2 because the y value is 2, right? So I multiply that's what I was going to do next. I take the formula and just do times 2 times this, whoop, and that's fine. And it doesn't affect everything else because 2 times 0 is 0, right? Is that making sense? Uh, and you code the same with the other ones. So for example, this one is going to be fun actually. This is going to be killed off because like the y value is 0, right? So like in this case, like because the y value is 0, you multiply it by 0, right? Like to force it to pass through that point. That's actually a good example. So that you see like sometimes like some of these will die off depending on the y value. So you multiply it by 0. Which of course, like destroys the entire polynomial. Okay, which is fine. Like that is allowed to happen. So that's good for you to see that can occur. And then for the next one, it has. I wanted to pass through the point, so I have to multiply by 3 to kind of like raise it up, increase the height to that point. So I'll do 3 times that one, and now it passes through that point. And kind of like the last one will actually be like a similar story, right? So if you look at the last one, uh, if you wanted to pass through 0, you have to squash it to 0, right? So it kind of destroys that polynomial as well. So kind of like the rescaled polynomials, the ones that are passing through the points, right, uh, are these 4, but actually because of the zeros, like the ones the second and fourth are not needed. So these are the only ones that are needed. And so kind of like the idea is that then you would add them together. But I'll still kind of like write down the formula by adding them all together. So you would do P0x plus P1x plus P2x plus P3x. And there you go. That would be the one that goes through all the points. But it's kind of interesting here because, right, if one of the y values is 0, basically that tells you that that point, like, doesn't contribute in the sense of their polynomial because their polynomial that we just found um, it gets multiplied by 0. But it's still useful to find that polynomial because imagine, and this is kind of what we'll do later in the week. Imagine there had been like an error in the measurement or things like that. So maybe the value is not quite 0, like it could be 0 plus some epsilon. So you want to see how things change if you change some of the y values a little bit. And for that, it's better to have these polynomials because if you change the y value, then you keep the same polynomial. You just multiply by a different y value in front of it, if that makes sense. So let me write that down. Sorry, let me go back to uh, um, here. Where is my iPad? So kind of like the answer, right? The answer would be is that the Lagrange polynomial we were after is kind of like a weighted sum of these polynomials. That's one way to think about it. Or like a rescaled sum of these polynomials. It's kind of like a rescaled, a linear combination. In fact, it's kind of like the another name that you can give for them. So it's like a linear combination. So it is, what is the formula? It is y, let me use the same colors. It's y0 times L30x plus y1 times L31x plus, you know, y2 times L32x plus y3 times L33x. So kind of like, because again, like each polynomial is value one where it gets activated. So and you stretch it out by the y value that you wanted to pass the polynomial to pass through. So, and in this particular case, just because of how like the numbers I chose, right? Again, let me see, what was, y0 was 2. So you get 2 times L30x, like, and then the other one was 0. And then 3 and 0. So in this particular case, because two of the y values are 0, it's just 2L30x plus 3L32x. And then you can kind of like, if you wanted, um, I mean, you can use like the explicit formulas to write down like something, you know, 2 times x minus 1 times x minus 2 divided by -6. Of course, I wouldn't expect you to combine them or anything, That is actually less like kind of hides more of the interesting information. So this would be a perfectly fine answer. But it is like a very elegant construction if you think about it. Um, is that making sense? So like what I'm trying to say is that in practice, once you have concrete points, there's kind of like no way, like it's not too bad to find the polynomials. uh, you can kind of ignore all this fancy notation. But if you think about it more from the algorithm perspective, if you were to write it as a program on a computer, then yeah, you do have to introduce all these extra notation so that like the computer knows what to do in every single instance, right? So that's why it's useful to kind of have written down the formulas in the extra notation. But in practice, like once you have a concrete points, like you just write it down. Um, So, okay, let's do a quick 5-minute break because now what I'm mentioning after the break is how useful this is of a tool. So I'll say a few comments about this, and maybe I'll say something else about the splines. If not, I'll talk a bit about the splines tomorrow. But I think it's a good place to do a mini break because I've talked for a while already. So let's say 11:40. I'll type it on the chat. But if still someone wants to ask me something, feel free to do so. Okay, so I guess we can continue um, discussing the polynomials. So kind of it's useful to have like a conversation of why you would like to use the interpolation. So the way I was like talking about the interpolation, maybe I should go back to like GeoGebra for a second. Where is GeoGebra? Okay. The way I was like I kind of like motivated the idea of like interpolating yesterday was by saying, well, maybe you're doing an experiment, you're like gathering some data, you know, and then you get like this number of points, right? And then you are trying to find like the polynomial that passes through those points, right? But from that presentation, like, the way I'm making it sound is kind of like the points are kind of like found without having a particular function in mind to begin with, but it is in practice sometimes useful to kind of like start with a function that kind of like generates a point. So let me give you an example of that, and I'll say a little bit of why that may be useful. So let me show you another. Let me continue going to GeoGebra, but open a different one. Um, okay. So for example, like you could have like let me see. Let's say you could have like a function like f of x. Let me use it. I'll just plot it from like for a finite number, a finite interval. So 1 divided by 1 plus x squared. Okay. So you could have like a function like this, right? Um, which is just like, okay, you can have like a function of like this, which is like a very normal calculus function. There's nothing crazy particularly about this function, right? Um, and you see the graph, and I'm just showing the values of the function for like x between -5 and 5, just so that we have like kind of like a concrete interval of like discussion. But so you could have this function, like, imagine you could try to find the integral for this function, like kind of like the definite integral for this function. Um, between -5 and 5, right? And okay, maybe you remember that in this case, like, that like what is the integral of 1 over 1 plus x squared? I think that has to do with arctangent, right? So you could try to do that, but of course, like then you would need to know the values for arctangent. So like an alternative way to try to do the integral, right, would be to say something like, okay, let me kind of like you have the interval from -5 to 5. So let me choose some collection of x values, so like I'll show them here in a moment. So I'll do them equally spaced. Okay, so how many points did I choose? I chose 1, 2, 3, 4, 5, 6. Okay, so I chose 6 points. If you notice, like all these points are at a distance two from one another, right? So those are sometimes that's called like equidistant points because they're like at the same distance from one another. So they're equally spaced. And so think of them as x values. So for each of these x values, right? For each of these x values, I'll find the corresponding point on the graph. Okay, so like the points on the graph would be -5, f of -5. Oh yeah, yeah, yeah. Like sorry, let me fix this quickly. It should be less or equal. No, it's fine. Then it would be -3 f of -3, then -1 f of -1. Okay, then 1 f of 1, then 3 f of 3, and then 5 f of 5, right? So what I'm trying to say is like, okay, you could have started, um, you know, you could have started, you have like the function, you kind of like choose like a number of x values, right? And then you find the corresponding points on the graph, right? And then what you could try to do is like, you could, let me just not show these points. So you could try to if you now pretend that you forget about the graph of the function, you kind of like have, oh, this is like a collection of points, right? Kind of like these data points that we were talking about now earlier. And you could be like, well, let me find the polynomial that passes through these points, right? So because if you found the polynomial that passes through these points, right, then you could integrate that polynomial from -5 to 5, and that could give you like a good you would like to think that, oh, that could be like a good approximation for what the value of the integral should be, if that makes sense. Okay, so it's kind of like the setup make reasonable. So what I'm trying to say is that sometimes like the points that you are trying to interpolate, they're not just coming out of nowhere. They may be kind of like generated from like a function that you know. Okay, so and then you would use a polynomial to maybe integrate it, and that use it as a replacement for what the value of the integral of the function would have been. So let me show you like what I mean in a little bit more detail. So let's see if I have it here. No, let's see. Is this the one? Oh, okay. Can everyone see? Eh, you can still see my Firefox, right? So here, like what you see is kind of like the so let's see. Well, we are thinking of it as kind of being like a graph of a function still in this context. So I'm thinking about the points never sharing the same x values, right? But if you wanted, like, for example, in the case of a circle, then you would just like keep like the upper half and the lower half, right? Um, so in this case, like so basically this is the example I was telling you about. So the orange curve is kind of like the function itself, right? And then you chose 1, 2, 3, 4, 5 points, right? I don't know if you can see the red points. Like, let me see if I can zoom my Firefox. Does it look better now? So like there are 1, 2, 3, 4, 5 points. So and then you find a polynomial, which is the blue curve, um, that approximates through those 5 points, right? So kind of like here, like the philosophy is like instead of like doing the integral for the orange curve, you would do the integral for the blue curve, because the blue curve is a polynomial and polynomials are super easy to integrate, right? Uh, now, so that's kind of like the setup. So you could ask, okay, what's interesting in this type of problems is like to ask, well, what happens if you kind of like had used more points to interpolate with, right? So again, because here I started with 5 points, 1, 2, 3, 4, 5, then roughly this polynomial that you see here, like the blue one, should be a degree 4 polynomial. Remember, the degree is always one less than the than the number of points. So for example, if I increase, oops, what's happening here? Oh, okay, cute. So okay, so what happened here is that I changed the number of points from 5 to 10. So you see now hopefully 10 points on the graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So the orange curve is still the same because that's the function, right? And then I'm using to generate the points. And then the blue curve is the polynomial that's approximating the graph, right? So the blue curve um, is in this case would be like, for example, degree 9, right? Because because again, it's always one less than the number of points. Okay, but what's a little bit interesting is to see what happens like if you keep increasing the number of points. Because remember, as you introduce more points, you're also increasing the degree of the polynomial in principle that you're using to interpolate, right? So let me see if I can show you 15. And that already something is happening here, right? Like, can I actually go less than 15? Like, or it only allows me to jump from, that's unfortunate. But it goes from 10 to 15. And I don't know if you see there's something going on, right? Qualitatively, right? What happens if I go from 10 to 15 points? It seems like it becomes a little bit wilder, right? Like it actually seems to oscillate more, right? And let's say if I put 20. Well, it's like if I could zoom out a little bit, like it would look better. But let's see. Ooh, okay, this is even better. And now with 25 points, like it kind of like is fluctuating even more, right? Let's see if I can put 30. Okay, so what I'm like kind of what I'm hopefully hoping to show you here, right, is that this is kind of like behaving kind of like opposite of what your intuition may have told you because you kind of like expect kind of like this philosophy of calculus that the more points that you add, right, kind of like the approximation should become better and better, right? But here what's happening is that the more points you are adding in the interpolation, right, kind of like the polynomial that you're using to interpolate is fluctuating more and more rapidly, right? Near at least near the endpoints, right? Like near the edges of the graph. Like kind of like in the middle, it's kind of pretty good approximation. But once you get to the edges of the interval, like it's kind of like fluctuating wildly, right? And this kind of like phenomenon is called the runge phenomenon, based on because this was like the person who first kind of like discovered this. So it is like I'll post these links on Canvas if you want to play about with them a little bit more. So it is similar to something that happens with Fourier series. If you have studied Fourier series, which is called the Gibbs phenomenon, which is sometimes like near the endpoints, like the approximation can kind of like start behaving a bit strange. So that is useful to know because and like of course like not that we're going to get into that, there's kind of like a theory that explains what's going on, right? Like so it's understood when this happens. Um, but kind of what I'm trying to kind of give you an example is that it is not true that kind of like the more points that you add in the interpolation, kind of like um, it happens like okay. So I'll kind of break down the answer. Like so the reason why it happens is because if you kind of find the formula for the error, right, between the function and the polynomial, that involves the derivatives, the higher derivatives of the polynomial, um, or like the higher derivatives of the function. I now I don't remember, but it involves the higher order derivatives. So, for example, if you're I don't know, like if you're using 45 points, it would involve like the derivative 46th derivative. Okay, but if the polynomial increases in degree, like the derivatives, just like think about the derivatives of a polynomial, right, of higher degree is like like the leading terms. Like you every time you take a derivative, you bring the exponent down and you multiply all these numbers. So kind of like the derivatives of the polynomials, the higher derivatives can grow a lot. So basically what the reason why it's happening, it kind of like because if you sample, this is kind of like the word for it. If you sample with equidistant points, which is what I'm doing here, because all the points had like this same value, same difference for the x values, kind of like the error estimate is involves like the higher order derivatives, and it's just like the case because you're using higher degree polynomials, right? That's the thing, like you kind of keep increasing in principle the degree of the polynomial. So if you had 100 points, it was 90 degree 99 polynomial. But if you had like what 1,000 points, it was a degree 999 polynomial, right? So the polynomial is kind of like changing, could be changing wildly from one step to the next, right? Uh, so because of that, that can kind of like make everything kind of like behave kind of in a very fluctuating way. Um, so kind of like well, first I'm showing you this because it's like an important thing to know. Like we're talking about numerical analysis, so it is good to have like an example that can kind of like shatter your expectations. Just because usually like the philosophy of calculus is like as n goes to infinity, everything should get better and better, right? But that actually is not true unless you know the errors, right? So everything kind of does depend on the error terms. um so that is the first thing to say. The other thing to say is that sorry, just to go back for a second here. Again, the way I was presenting this calculation, the way I was finding these points is that these points, like they are all at the same distance on the x-axis. So again, they're equally spaced points, which are called like equidistant points. There is another way of generating the points, which I'm not going to get into, which are called like the Chebyshev points. Um, Again, I'll post all the links on Canvas if someone wants to learn more about this. But basically, the way the Chebyshev points are found is that instead of like separating along the x-axis by the same amount, you kind of like take a circle and you separate the points on the circle by the same amount. So kind of like the lengths of these arcs are equally spaced. and then you look at the projection of these points on the circle, and that's how you would generate the distribution of points. Again, like the details, like you can read about them if someone is interested. But kind of all that I'm saying is that there's like an alternative way of generating the points, which is not like equally spaced in the x direction, but with using these Chebyshev points. And if you do that, actually, this does behave a lot better. So, for example, like now this is kind of like the approximation using Chebyshev points. And what happens, the way they're constructed is that they kind of like tend to accumulate more towards the edges of the endpoints rather than like, equally spaced. So if you increase the number of endpoints, the number of like points in the approximation, like you see, like this is behaving way better. You know, this is behaving way better than what we had before when we were doing the equally spaced case. So even here, it's not that like the Lagrange interpolation always fails. It's just that it can behave poorly if you don't use the correct spacing for the points. Okay, so that is also like a useful thing to understand. And there's like a thing called the Chebyshev polynomial, which is similar to the Fourier polynomial and the Fourier series stuff. So again, I'm not going to get into those details. Like, the way I'm going to give you the problem of a Lagrange polynomial is I'll give you the points from the beginning, kind of like 3 or 4, so that it's kind of like realistic for you to work on them. And then you find uh, oh, right, right. No, no, it is still like a 99-degree polynomial. True. Right, right. It's still kind of like the degree is higher, it's still high order, but it's just that because the kind of like they think, like the difference is that the space, you see, like the points kind of like accumulate more towards the edges of the interval, right? So that since there are more points towards the edges of the interval, that kind of like forces the polynomial not to fluctuate too much. I mean, it's all very like heuristic, intuitive how I'm trying to explain it, but kind of like the idea is that because the spacing of the points is not the same distance, you kind of like the region where it was supposed to give issues, right? The place where it was going to give issues was kind of like towards the edges of the interval, but that is kind of you're imposing more controls on that because there are more points that it has to pass through towards the edges. But it's still true that it's kind of like a high degree polynomial, but it's just like the error term is different. Like the error term, if you use Chebyshev interpolation, just has like a different shape than equally spaced. So when I said that it involved the derivative of the polynomial, the higher order derivatives, I was referring to equally spaced um, interpolation. Like with the Chebyshev points, it's like a different error calculation. But kind of like intuitively, what's happening is that you have added kind of more points towards the ends, and that kind of like gives you a better deal of the situation. So like for example, this one, like if you look something like this, it's like it's almost indistinguishable from the graph. So again, I will post this link on Canvas, but if someone like wants to read more about that, I did post it on modules. I'll probably be doing this like over like the course. Like I posted, where is it? I posted like a module called extra reading. Um, so there's like this is like a very nice article. It's not too hard to understand. Like you could with what you know of mathematics, you could totally read it. But it's kind of like useful because it kind of like talks about like these misunderstandings that you could have when you're trying to use Lagrange interpolation or just like these polynomial approximations to do things. So it kind of like goes into more detail than the one that we're going to spend in class for like discussing like oh what is a correct strategy that you would use if you had like a concrete realistic problem. Again, like the way so you can kind of like read it on Canvas, like you can download it also, like that's like it's not a problem. um but it's kind of like a useful thing to know because like again like there's like a difference between how we're dealing with these problems in practice versus how you would deal with them in real life. And so it's kind of like useful to know that that there are issues that can arise. So like if you want to learn more about them, like the I will leave those sources on Canvas. um what I was going to say is that for our purposes, the way we will do in practice is like I'll give you 3 or 4 points and I'll ask you just to find the Lagrange polynomial through those points, right? So of course those things you never notice because you only notice them once you have tons, like thousands of points or like way more, right? So like that's kind of what I wanted to show you about. Uh, and I think it's like like I think it's like a good place to end here. But it's just for you to have like some more like perspective into the topic, and also of why you would be interested, in doing this type of stuff. So tomorrow, what I will talk about is a little bit about splines, which is an alternative to an alternative construction instead of using like a Lagrange, like this polynomial, to kind of like break it into cubics, like which is like a very useful thing as well. So we'll do some spline stuff if that sounds good. I'll stay around like if someone wants to ask me anything, but I think it's like a good place to end to not go overboard with today's class. Bye. Let's see. Let me check. Oh, true. I had put the deadlines for Saturday, right? Let me check the right. I forgot about that. So when was the first deadline due? Oh, it would have been by okay, so I'll move it to the 19, right? You're right. Yes. Let me change it now before I forget. Uh which is oh, it's called homework one, right? So I'll move that one now to 19. I'll probably put the next one not soon so that people can work on them as well. Good. Anything else, or what? That was the only thing you wanted to tell me. Okay, perfect. Okay, good. Okay, I'll see you tomorrow then.